The math over here, and today we're going to be looking at the 1983 AIME problem number 5. And here's a view of this problem. Suppose that the sum of the squares of two complex numbers x and y is 7, and the sum of the cubes is 10. What is the largest real value that x plus y can have? Well, first we're given that x and y are complex numbers, so let's maybe note that, let's just call x is equal to a plus bi, and then let's call y equals c plus di. Okay, and what is the largest real value that x plus y can have? So let's first evaluate x plus y, and then using basic complex arithmetic, that's just a plus c plus I times b plus d, and then we want this to be real, so the imaginary part has to be equal to 0, meaning that b plus d is equal to 0, or in other words, d is equal to negative b. So we can actually maybe like transform this a tiny bit to x is equal to a plus bi, and then y is equal to c minus bi, and then we have something a little bit more like better. But okay, so now let's implement some more conditions. We're given that the sum of the squares of the complex numbers is 7, right? So let's just write that. We have a plus bi squared plus c minus bi squared is equal to 7. Expanding this out, we should get a squared plus 2abi minus b squared plus c squared minus 2bci. No, that's b squared, I squared, that's minus b squared. This is equal to 7. Now this is real, so we know the imaginary part of this will also be equal to 0. So looking at the terms, we see that there's a 2bi common in both of them. So we can factor in that imaginary part as follows. We can do 2bi, and then we can do a minus c. This is equal to 0, and great, that gives us that a is equal to c. A is equal to c. Okay, so since a is equal to c, we'll then transform this again to x is equal to a plus bi, and then y is equal to let's see, a minus bi. Okay, now we see that x and y are complex conjugates, and I think we can now attack the final constraint that the sum of the cubes is 10. Alright, so let's do that. A plus bi cubed plus a minus bi cubed, is equal to 10. Now you probably may know a formula for x plus y cubed plus x minus y cubed, and that just happens to be that the even terms cancel out. But let's just expand this for thoroughness. We get that, what's this? A cubed by binomial theorem plus 3a squared bi, and then this becomes minus 3ab squared, and this becomes negative b cubed I, and then plus, now we do this part, which is just a cubed minus 3a squared bi, and then this is just our usual negative 3ab squared, and then this becomes, however, this becomes plus b cubed I. Okay, and then now stuff cancel, as I said. The second and fourth terms will cancel out, so we're left with 2a cubed minus 6ab squared is equal to, sorry, this is my first day with the software, so like, sorry if the writing is a little bit messy and it's taking a long time, but let's just continue with this. Let's factor this maybe to get 2a times a squared minus 3b squared. This is equal to 10. Or in other words, we have a times a squared minus 3b squared is equal to 5. Now if we can solve for one of a or b, then we're good. And so that brings us to this thing over here. We forgot to equate a is equal to c here, and if we equate a is equal to c, what happens is we get a is equal to c. We just substitute a is equal to c to get a squared here. So the real part of this thing will be 2a squared minus 2b squared. This is 2 times a squared minus b squared, and we know that this is equal to 7. I should have done that step sooner. but that comes from the motivation that we need to solve for one of x or y, I mean a or b. Okay, so now what we need to do is let's just solve for b squared in terms of a squared, right? We just divide both sides by 2 and then isolate b squared to get b squared is equal to a squared minus 7 over 2. A squared minus 7 over 2. Great. So this becomes a times a squared minus 3a squared, and then this becomes plus 21 over 2. So okay, hold on 1 second. So sorry if I'm I'm just showing all the algebra to be thorough. So this becomes a times negative 2a squared plus 21 over 2 is equal to 5. A times negative, there, this looks right. Okay. Oh my god. Okay, so negative 2a cubed plus 21 over 2a is equal to 5. Bring everything to the other side to get 2a cubed minus 21 over 2a plus 5 is equal to 0. Of course, there's nothing fun about a fractional part, so we'll just write it, multiply both sides by 2 to get 4a cubed minus 21a plus 10 is equal to 0. And now we need 100 for a's to let's satisfy this. By the rational root theorem, we can quickly see that a is equal to 1 will give us negative 7. 2 will give us 2 will satisfy, because we get 32 plus 10 minus 42, which is equal to 0. So if we do synthetic division by factoring out 2, we'll get our desired thing. So 4, 0, negative 21, and 10. And then doing it, we get 4, 8, 8, 16, negative 5, negative 10, 0. So this factors as follows to a minus 2 times 4a squared plus 8a minus 5. So now we can solve for a is equal to 2 or a is equal to solutions of this, which is 64 plus 80, 144. Negative 8 plus or minus the square root of 64 plus 80, 144 by 8. So negative 8 plus or minus 12 by 8. So we have negative 28. So a is equal to 2, 1/2, or it can also be equal to negative 5 over 2. But now note that what is the largest real value that x plus y can have? X plus y is nothing but 2a, right? So we want to find the largest value that 2a can have, and that happens when a is equal to 2. So 2a is equal to 4, and we are done.